Hey everybody, today's lesson is the last section of this graphing rational functions section, and we're talking about oblique asymptotes today. So I want to draw your attention back to the very first day when we did all these asymptotes and all that stuff. What you wrote down under the horizontal or oblique slant asymptote section is how to find them. And the first one we've done already, when the degree of the numerator is less than the degree of the denominator, that's when the horizontal asymptote is the line y equals 0. The second one, which we've also talked about in class, is when the degree of the numerator is equal to the degree of the denominator, like this example right here. That's when you just do the lead coefficients, and that's your y equals, in this case it was y equals 1. And then option number 3 is the one that we haven't talked about yet. That's when the degree of the numerator is bigger than the degree of the denominator. That means you do not have a horizontal asymptote, you have a slant asymptote, which is called an oblique asymptote. So that is the third case, and it's actually not a horizontal line. It is a slanted y equals mx plus b line. So that's what we're going to be talking about today. So now I'm going to pause the video, flip to the oblique asymptote section, and start filling some stuff in. Alright you guys, so here we are on our oblique asymptote section, the very last part of the packet. And so just like I was explaining earlier, when the degree of the numerator is bigger than the degree of the denominator, that means you have an oblique asymptote. So look at all of these examples down here. The degree of the numerator is 2, the degree of the denominator is 1. Same thing here, 2 and 1. Same thing here, 2 and 1. So in this case, it's not a memorization, it's not a lead coefficient thing. Here's what you do. You use synthetic division to find the equation of the oblique or slant asymptote. It's going to be a y equals mx plus b type of line. And just remember that you ignore the remainder if you have one. In synthetic division, a lot of times you have a remainder, and in this case we're going to ignore it. So what I'm going to do is I'm going to do synthetic division. I'm going to do a division problem like we did in the last chapter for this. So remember, you start by equaling the denominator to 0, so I'm going to use -3 in the box, just like we did last chapter. Line up the coefficients of the numerator here, which are 2, don't forget the 0, and -6. Bring down the 2, gives me 18 and 12. I have a remainder in this. Remember, what we're supposed to do if there is a remainder is ignore it. I'm going to ignore this 12. And that means that my oblique asymptote is y equals 2x minus 6. And this is what I'm going to put on my graph as a dotted line like the electric fence. There's not going to be a horizontal one for this problem. There is going to be this line as a dotted line that works as the electric fence. Okay, same thing for number 9. I'm going to put -1 in the box and line up the coefficients and just do synthetic division. Again, we have another remainder. That'll happen a lot of times. You ignore it. And that means that the oblique asymptote in this case is y equals 1x plus 3. And I'm going to put this as a dotted red line on my graph. And that's going to be the electric fence or the magnet that my graph is attracted to. Same thing for number 10. I'm going to put +2 in the box. Remember, that's because you equal the denominator to 0. I'm going to put -1, -1, and yes, I need a 0 for the constant term because there is no last term in that polynomial up at the numerator here. Go ahead and do the synthetic division. Again, we have a remainder, but we ignore it for this. This means that my oblique asymptote for this problem is y equals -x minus 3, and that's going to be my dotted line that I'm going to use when I'm doing that graph. Okay, let's take a look at number 11. We're supposed to do the whole thing. So, in this case, again, we're going to start out the problem by doing the exact same stuff that we've done at the beginning. The vertical asymptote comes from setting the denominator equal to 0. That part has not changed, and that means that my vertical asymptote is the line x equals +2. And so in this case, I know that I'm going to have an oblique asymptote. So I don't have a horizontal asymptote, I have an oblique one, and that is because the degree of the numerator is bigger than the degree of the denominator. So in that case, what I need to do is synthetic division in order to find it. So I have 1, don't forget the 0 and 1, doing the synthetic division. Ignore the remainder. This means that my oblique asymptote is y equals 1x plus 2. And those are my two asymptotes that I'm going to put as dotted red lines on my graph. I'm going to go ahead and do x-intercept and y-intercept as well real quick. For the y-intercept, you plug in 0 for x. So it's going to be 0 comma something. I'm going to do that off to the side. I have y equals, when I plug in 0 for x to the problem, I get 0 over -2, so -1/2. And when I do the x-intercept, that means set the numerator equal to 0, aka plug in 0 for y. I'm going to do that off to the side. I have x squared plus 1 equals 0. That means x squared equals -1. When I square root, I get I. That means I do not have an x-intercept, so I'm just going to put none. Okay, for wholes, remember that means point of discontinuity, so remember how to do that. That only happens if you have factors that cancel. And in our original problem here, nothing factored, nothing canceled, that means that I have none. Okay, and remember the test for if it crosses the horizontal asymptote or the oblique asymptote. That works the same exact way. What you do is you set the original function equal to the horizontal or oblique asymptote, and then you cross multiply and solve. So I'm going to do that work over here off to the side. I'm setting the original equation, x squared plus 1 over x minus 2, and I'm setting it equal to my oblique asymptote, and I'm just going to see if I can solve. So what I'm going to do is put the x plus 2 over 1, cross multiply. I get x squared plus 1 equals, when I cross multiply this way, my middle terms cancel out, and I get x squared minus 4. And notice what happens here, the x squareds cancel on each side, so I get 1 equals -4. Okay, that doesn't make any sense. I'm not able to solve that equation. That means that it does not cross anywhere. I do not have a cross of my asymptotes. So all I have to do here is I'm going to start by just graphing all the stuff that I've gathered here in this table. I'm going to graph the line x equals 2 as a dotted line. I'm going to zoom in a little bit so it's nice and neat. X equals 2 happens right here. Bear with me while I zoom in and out a little bit here. I'm going to graph the oblique asymptote as a dotted line, y equals x plus 2. You guys all know how to graph that line, x plus 2. That means you start on 2 and you go up 1 over 1. So it's this line is my oblique asymptote. You can dot it if you want to. I'm actually going to draw little dashes. But just make sure it looks like your normal asymptotes do. Keep going this way. There's that asymptote. So it's the same as a horizontal asymptote, obviously, except now it is slanted. What about intercepts? So my y-intercept is 0, comma, -1/2. So 0, -1/2 goes right here. And as far as the x-intercept goes, remember how I said there were none? That means that my graph cannot go through this point through the axis because I do not have any x-intercepts here. So that makes this part really easy because the dogs still run up towards the asymptote, they just don't go through it. Remember, we found that it did not cross the asymptote, so here's what my first section is going to look like based upon using that y-intercept and the fact that I did not have an x-intercept. So it looks kind of like a parabola, just a little bit of a slanted one. So only other thing I need to do now is come up with one other point on this graph so that I know whether my graph is here or whether it's here. So I need to just figure out, I need to pick some kind of an x value over here in this category just to find where the other part of my graph is. I know for a fact it's not up here because that would make my graph not a function. It would not pass the vertical line test if I had a section of the graph here. So my options are, is the other swoop up here, or is the other one kind of running up along next to it like this? So I'm just going to pick one x value in there. I think I'm going to pick 3, because 3 is in this category over here. It'd be easy to plug into my graph. Just making a quick t-chart, what happens when I do an x value of 3? And again, I'm using this original function up here. So that gives me 3 squared plus 1, which is 9 plus 1, which is 10 in the numerator. When I plug in 3 to the denominator, I just get 1. So the point 3 comma 10 is on my graph. That's just doing a basic t-chart, you guys. So I'm going to go to my graph, find the point 3 comma 10. So 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 is way up here. That tells me that the other swoop of my graph looks like so. Again, more points give you a more accurate graph, but I know it does not go through this electric fence, so it's going to be lining up right next to it, attracted to it like a magnet, but I know that it's not in this section of the graph, it's up here, and that's because I found the 0.3, comma 10. Okay, so only new thing there, you guys, it was the exact same as all the problems we've been doing, except this asymptote now is slanted, it's not perfectly horizontal. That's the only thing. We'll do the very last problem in the packet together in class tomorrow. Thanks for watching. Have an awesome night.